Okay, should be any second now.
Got it.
Ah. Well, as our outreach coordinator just said, we're going to yak for an hour. Let's get together, everybody. The Astro Unit gang is on the air on the new. My God, it's just the greatest thing in the world. Virtual getting together again for a Monday morning trip through space, covering everything from NASA missions to cosmic objects, star clusters, galaxies, planets, the moons, recent discoveries. Boy, you're going to hear some stuff today you won't believe. I'm Ron Heron, Vice President of the club. I'll introduce you to the rest of the board here in a minute. It's the SBAU Astro Hour number, I believe, 95, from Monday, December 19th through Christmas Day, next Sunday, December 25th, 2022. All done live from our computers, rooms, man caves around town, and all for the Santa Barbara Astronomical Unit. I'm ready for the topics. Let's talk about a white dwarf sucking up its binary neighbor's stuff, giving us regular light shows. There's a comet occulting a star this very morning. We have proof of that, I think. Going to talk about at least one nebula and a visible star cluster. Talk about some nuclear fusion finally being made. Could be the wave of the future, and some new theories that are just going to blow your mind. Ladies and gentlemen, meet the president again for his 5th or 6th. How are you doing, Jerry?
Good. Good morning.
Jerry Wilson, the man behind the cartoons that he sends us. His wife is Pat Forgy. She's also a stalwart member. Outreach coordinator, the best there is, Chuck McPartland, in front of his Ukraine flag. His wife is our lovable merchandise manager, Pat, also married to a Pat. We have Tom Whittemore on screen joining us, former Westmont College science instructor and incredible editor of our SBAU newsletter and baker of incredible sourdough bread. Gentlemen, you heard what we were going to talk about. However, we like to start our SBAU Astro Hour with a little levity and humor, and I write down my comments and then I can never find them when you call them up on screen, because I've tried everything. Oh, there we go, a bunch of dinosaurs. Oh, that was last week, I see. The best medicine cartoon shows the dinosaurs looking up. Sadly, the enthusiasm of the Ancient Reptiles Astronomy Club was short-lived because I was a big one. Oh, look at that big one coming in, Charlie.
Yeah.
I wonder where it's going to land. Here we go with more. They're looking at the wall. You know what? I don't remember some of these. It would appear the asteroid struck during a book signing. They got pictures of it on the wall. I did not see that one. I don't think you sent that to me. Did the rest of you guys get this one?
I don't recall that one.
I don't remember that one.
Okay.
It's not a wall, it's an excavation.
Yeah, with a fence around it.
Yeah.
They're looking in a hole.
Yeah, okay, a book signing. Yeah, all right. Enlarge that one too, because I'm not sure. You may be a week behind, Jerry. All
Oh, did
right.
I show this before?
No,
No, but-
this is new.
This is
Okay.
all
Whoops.
none of the ones that I have. Let's see. I guess Angel is talking to God. You should really clean up your desktop, Lord. There it is in space. My God. I just always wonder. Here we go. Oh, this one I got. Man in shorts stands next to the alien. I'm not sure if he knows about it or not. Middle-aged couple taking pictures. She says, "Yes, Warren. Already, my dear. There is film in the camera. Invisible. Do they not know it's there? Is that the deal? Is that
No, she's
The joke here is
Being
that she wants
exposed.
to get documentation of the alien, and she opens up the back of the camera to verify that there's film.
which ruined all his pictures.
Right.
Yeah, along with the swamp gas that's always at those events. Wow. Okay, that we're now on track for the ones.
Now
that are-
this is you'll notice I think this is a Far Side,
Yes.
Oh, yeah.
and it's from 1983. So this was before digital cameras came in.
Yeah.
You suppose that Larson gave it up just because he ran out of ideas or got tired of?
I didn't know he gave it up.
Yeah, he gave it up for a while. He was tired of having to grind one out every day.
Uh-huh.
And he went into his fun hobby, which was marine biology. And
Oh,
he was doing that for a long time. And then he said he avoided digital. You know, a lot of the cartoonists went to using digital drawing.
Yeah, I remember
And
that.
He didn't like that. And then somebody gave him an iPad. And he
Oh.
started doodling on that and decided he liked it. So he's producing stuff again. I just don't know if he's publishing it.
Doesn't call it the far side. Well, here we have a guy in the pharmacy trying to decide between placebos or the new fast-acting extra strength placebos. Better go with those, I think. They're cheaper. And the placebo is defined as something that they give you that doesn't work, but you don't know it.
Right.
And here the man is sampling his pile of... What?
It's right from the Latin. It's right from the Latin. It means I will please. I shall please.
Okay,
Yeah,
so this one... All right, we're going to get a lot from you this hour, Tom Whittemore. Gentleman and his wife, I guess, having an Italian dinner, big pile of pasta. The noodles are scrolling around into a coil, and she says, I told you not to order the Fibonacci, which is that the name of a scientist or?
No, it's the name of the spiral that the pasta is taking.
The Fibonacci fractal? Is it a fractal?
No, it's a Fibonacci spiral.
There are Fibonacci numbers, Ron. Fibonacci.
Yeah. He's a mathematician, and you can see the little comment down below. It says, bet his dish is better than the last two combined.
Yeah.
Because the Fibonacci sequence is starting with 0 and 1, and then each next number is the sum of the two previous ones.
Right. 1, 1, 2, 3, 5, 8, etc.
And so that's a different kind of a spiral than the ones we normally see.
No, it's just a specific spiral.
Yeah.
Surprisingly, Fibonacci was originally studying rabbits and how many they produced, and it led him to this wonderful sequence of numbers.
And he was an Italian scientist?
And yeah, definitely Italian, mathematician, like Chuck said.
Wow, okay. You'd have to really be hardcore to know that. All right, couple of frogs are resting on the stovetop in a pan, which is their own little hot tub, and relax, says one. Pot temperatures have been going up and down for centuries.
This is a dig at climate change deniers.
Yep.
Pretty good.
All
now,
right.
you recognize the artwork here. This is from the artist from Mad Magazine, which I was a big fan of when I was a teenager.
I used to know who that was, and I recognized it right away. Yeah, I guess this came from Mad. He only did Mad stuff. So the ancient Romans coming out middle of the morning, I guess, to check on their timepiece, which is, of course, the
sundial. And he's taking out his key.
Okay, he winds it up, and that means up goes the sun. It pops up real fast. Has to go an hour up because what is daylight saving time? Is that what it is?
He might be making that adjustment.
Okay. Funny stuff. What do we got? The Flat Earth Society has the same time on all the clocks around the world.
Pretty good.
Somebody named Hankin.
Yeah.
All right, we're back at the beginning of Best Medicine. We're zooming out here, ladies and gentlemen. Well, if you want to save till the end when we get silly with all the new discoveries and thoughts, and well, they're not discoveries, they're just theories that rival the string theory as far as I'm concerned. But you got up early this morning, Chuck. Did you too, Mr. President, to check out that occultation?
No, I was.
Do we often have an occultation like that, a comet going in front of a star? Does that ever happen?
Yeah, there's a whole feed for that. It's tough because, comets are constantly outgassing. So that's like having a little jet engine. And so the orbits aren't well enough defined to often say, basically the reliability of the predictions is very low because the comets are moving around more than something that's just strict gravitational motion. But this one, apparently the prediction was good because they had an occultation of this comet passed in front of a star last week, and that allowed them to really update the orbit. And so they had a prediction, and it was going along through Southern California, and it was just off the coast for us. So I was in the 1 Sigma region. I recorded it, but I have a small scope, so I don't know if I managed to get useful data rates on it, and I didn't see anything obvious happening in it. But I have some images from it if you want to see them.
Yes, please.
Yeah.
All right, is this the RSOPU Chi binary? No, that's the other. That's the.
No, this is a 12th magnitude field star. It's at the center of this bullseye. You just plug the right ascension and declination into my planetarium software, but it doesn't show the actual star. but it is in Gemini here. I'll stop sharing so you can share.
Okay.
Okay.
I clicked a little too soon. Let me try that again. Okay. Da-da-da-da-da-da-da-da.
It's going to be your pictures.
Yeah.
Fantastic. Put those in the archive, Tom Totten. He's our webmaster normally.
All right. It was fun to see him on Friday night at Westmont. I haven't seen him in a while.
Really?
Yeah, he was out on the deck entertaining folks about Andromeda with his laser pointer.
Wonder where our spam collector guy is.
Are you able to share?
Okay. Boy, for some reasons, it's not letting me share. It's telling me I have to quit Zoom and rejoin if I want to share my screen.
Oh,
Anyway, I did video it. I could see the coma of the comet, but basically by the time I was getting ready to record, the images of the comet nucleus, the pseudo nucleus, and the star had merged. So there was just one blob there. But you could see this haze around it. I had a lot of problem with my power cables. I had to go through 3 power cables before I got one that worked and powered my camera. So I got my recording late. And interestingly enough, I did see what looked like a brief occultation, but of a completely different star in the field. So maybe there was a bird or a bat flying over or something like that. But my target guy didn't show any obvious occultation. There was a low drop. I think it was a little bit early relative to the prediction, but it was only, well, 1, 2, 3, 4, 5, 6 readings. So I'll have to see. There are 2 people that did successfully record an occultation, one of them 3.3 seconds and one of them 1.5 seconds. And they were kind of on either side of the path, but within the shadow path. So we'll see if my stuff jives with any of that.
okay.
This occurred at 3:50 in the morning.
For me, it was at 3:46.
Okay, so Gemini was well overhead, if not on its
it
way.
was, yeah, in the west, kind
Yeah.
of high in the
It was
west.
well placed.
Yeah.
But by the way, just for folks listening, you can now easily see Venus after the sun goes down in the southwest.
Mercury still hard?
Yes, I did not see Mercury, but Maureen and I both saw Venus last night, shortly after 5, and then longer after that too.
Okay.
Very easy pick off. Very easy to pick off.
There's a guy that has a brief astronomy column in Newsweek, in Newshawk, and he shows a graphic of Venus and Mercury in the west immediately after dusk this week.
Yeah,
So-
for the
good, good.
24th, he shows a crescent moon near them to help find him.
Yeah, that's right.
Good, good. I'll pull out the binoculars tonight.
Okay.
Well, just for the record books, this is Comet 2019, the Schwarzman-Walkman variety. And can you enlarge that picture at all a little bit, maybe one step without the monolith covering it there, Jerry? Just curious. That's not our sky. There you go. There's a lot of stars in a totally beautiful sky like Wyoming or Alaska. Where
Now this is showing, this is from the planetarium software. So a lot of these streaks are galaxies, they're not stars. The bright points like this, that's a star. This is some kind of a, well, I don't know what that, brighter star. There, this is hallmark clusters. So not everything's a star here.
But
And Jerry, I just want to mention a nod to your mentioning Colander 463. It was a hit at Westmont on Friday night. I pulled it in. So it turns out that the database for the telescopes at Westmont not only do Colander objects, and we got 463. It's really neat. It also does stock. It does stock objects. So I pulled in a couple of Jürgen Stock objects.
okay,
That's it.
the red lines and we missed it. I have one last question about that.
Oh, you want to go back to this?
Yeah, my question is this: there's so many stars up there, and here is a comet which always traverses the sky in a certain orbit of its own. It's never stuck like the stars are. You would think there'd be a lot of occultations, wouldn't you? Sooner or later.
Depends how dim a star you want to look at.
Mhm.
Well,
A comet surely presents a bigger target to occult than an asteroid does. And some of these comets have such big and long tails that you can see stars through their tails. So technically, I guess that's an occultation.
Yeah.
But they're really more interested in the nucleus.
What if it were going to occult a distant galaxy? Would they tell us and let us know? And is that a big event? It's just stars. Okay, and real quickly, what do you know about Comet 29? Is it going around the sun? Is it coming in our side, inside our orbit? Or?
It's in an orbit beyond Jupiter that's fairly circular, so it pretty much stays out there. But it has periodic outbursts. It seems to have, this is the one that we talked about last week that has the cryovolcanoes on it.
Okay, so it does exactly what some asteroids do. It's got its own little permanent orbit. It's not going back out into the Kuiper belt, right? Okay, it just happens to have a lot of water on it, so that it
as permanent as orbits get. Yeah.
Okay, let's go to that next picture then, and we'll see what that's all about here. What are we talking about here? What's this?
Here we're talking about the rich field of Coma Berenices. There's boundary lines of Coma Berenices, these things here.
There it is.
It's loaded with, it's also in, has in it a galactic cluster, and that's most of what you see for the galaxies around here with a couple of star clusters. But the major topic here is Melote 111, which is this rather large loose association of stars, which is actually a star cluster. And that's what the text in our talking points refers to most.
And this is early morning. That's kind of what was up when I was at 3:45 this morning.
Me too.
And this shows a photograph of Melote 111 taken by an astronaut out the window of the ISS.
It's pretty good.
And this association of very bright stars here is that loose association. It's a cluster, an open cluster. It's pretty close to us, and that's why it's so big. And the stars are in the process of scattering from their nursery. They've blown all the gas and dust away that formed them. And now each star in the cluster is in its own different orbit around the core of the galaxy. And as they go around in their orbits, they look like they just scatter and disperse.
So they're not a cluster anymore.
They are, well, until you can't see them all in one association, yes.
Jerry, isn't it true the Melote catalog is just open clusters? Yeah, okay. Just like the colanders.
Yeah.
Okay.
Do you suppose the big heavy duty dictionaries they've come out with every year have terms like star clusters and they define it, since the two words apart would not tell us anything other than a star is a star and a cluster could be anything? But are they defined as orbiting each other, all the thousands or dozens or scores?
Well, they're gravitationally loosely bound.
They are. Unlike the rest of, I mean, just because there's a bunch of stars, within a few light years of each other, they're all going in the same direction around the Milky Way, wouldn't make that a cluster unless they're orbiting each other as well, right?
Well, orbiting a common center of mass, I guess you could say.
Yeah.
Okay.
Now this one appears to be moving with us around the galaxy as we rotate the galaxy around the galaxy. So it's pacing us.
Yeah. So Ron, it'll have a streaming velocity.
Okay.
Yeah.
The further out from the center we are, the slower we go, or just we lag behind. We're in the trailing ends of the arm. No, we're in between arms, aren't we?
Just like an orbit, any orbit, the further it is from the center of mass, the slower it's going.
We're in a
higher energy, but slower speed.
Okay. Understand. We're in the Orion Spur, right?
Yes.
Do you suppose this is too? Do we see stars inside the arms? Or
it's fairly close to us.
Okay. Fascinating stuff.
Yeah.
Coma or Berenices, open cluster, visible to the naked eye as well. All right, you're jumping around, so we're going to save all those strange new theories to last.
Let me point out one feature. This is a photograph, like I said, from the IS. It's a single frame photograph. And if you use a DSLR camera and you take a single frame photograph, all this modeled background is is non-uniformity in the responsivity of the detectors in the field of view. It's sometimes referred to as fixed pattern noise. And you take multiple pictures offset from each other and you add them together, and that gets rid of all this noisy stuff and shows a real nice clean background of black. But this is a single frame, and you would get the same thing from a single frame.
It looks like there's some air glow down there at the lower right too.
Yeah, I was looking at that, sort of greenish, like air glow. Some cameras, like early Canons, had what Tony Hallett called the Green River, and it was a band of greenish stuff that went across the focal plane like this, and it was due to internal light from the camera. When you make a detector, it's just a gate, an electronic gate in silicon. And there's a lot of other electronic gates in the circuitry. And every one of those gates, if you run current through them, it can act as a little light source. And they didn't, in the early digital cameras, they didn't effectively block or hide that source of light.
Huh.
Another cool thing, Coma Berenices, the North Galactic Pole is in there.
Oh, yeah.
And so that's why when this is high in the sky, the Milky Way is going right around your horizon.
Yeah, yeah.
You lost me. The North Galactic Pole. What is that?
Well, that's like the equivalent of our North Pole, but for the galaxy. It's the rotational axis of the galaxy.
Right.
And you pick call the north one the one that's closest to our north. And it happens to point right up there in Coma Berenices. And so when that's overhead, you got the Milky Way galaxy going right around your horizon.
Oh, I see. Okay. It's also known as Melade 111, named after another.
That was the cluster. This is not the cluster. This is a galaxy. This is Messier 100.
Oh,
I put in a couple pictures in Coma Berenices. It's the galactic cluster, the Coma cluster. And this is one of the brighter objects, Messier 100, in Coma Berenices. It's just a very pretty picture.
It's beautiful.
And then we also have
the black eye?
The black eye M64. And look at how much dust this thing has. This is a popular object with amateur photographers and astro imagers. There's so much dust, and so on this side, it obscures the bright core.
Mm-hmm.
So there's a lot of star formation going on in this.
Right.
And of course, there's random galaxies, a lot of faint galaxies in it that aren't M objects. This is just a random part of the Coma cluster. And you can see that there's different colors of galaxies.
Oh.
This one has a real bright bluish tint to it, which is taken as an indication that this one has recently been disturbed by proximity to another galaxy.
Wow. We given all those names?
No, they all have numbers.
Sure.
This is a, it's a little low resolution there. This is an irregular galaxy. See if that has a name. That is NGC 4789A. So for you name fans.
Ooh.
4565.
That's right.
That's right, 4565, the Needle Galaxy.
Right.
Which we're obviously seeing edge on.
Yeah, and all these are in the cluster. The next one,
Uh-oh. Brightest stars, there we go.
I guess I missed one. So anyway, you won't see that one because it's out of order. But we can go to the Astro photo of the day, the APOD, for yesterday, Sunday. And it displayed a frame that contains the 25 brightest stars in the night sky, both northern and southern hemisphere. I'm not familiar with the southern hemisphere, but they have one down here called Mimosa.
That's in the Southern Cross.
Okay.
Yeah.
And then there's Gacrux.
That's in the Southern Cross.
Okay.
Yes. Yeah. Yeah. Chuck keeps.
Yeah, there's a bunch of them. Adhara, Shaula.
No, Shaula is the stinger of Scorpius.
Scorpio.
Okay.
Acrex is the Southern Cross.
Okay.
Got a companion.
I didn't realize the Southern Cross was this bright.
Yeah.
Sirius, of course, being the brightest up in the upper left.
Yes. Canopus a close second.
Yeah.
And that's,
In
that's
Santa
Alpha
Barbara,
Centauri there, Rigel Centaurus.
Mhm.
in Santa Barbara, we can almost get Achernar, but we can't
Okay.
quite.
So the APOD discussion of the APOD photograph was discussing this for names, because these things are so bright. They have been given names from ancient times, way before there was any telescopes, just from people camping out in the sands of Arabia. And I guess Sirius is Latin for the scorcher.
Right.
Vega is,
I think it's Greek, right, Chuck?
Right. Both
Yeah.
both Latin and Greek, but the Latin version is a version of the Greek version. So the Greek was
Okay.
earlier.
Okay.
Vega is Arabic for falling.
I think it came from swooping eagle, so it's probably
Yeah.
Okay.
Yeah. Yeah. It has a
Little
sense of,
poetic license here in the caption.
Well, they're
And
cutting down on the number
Antares-
of words.
Isn't Betelgeuse the devil?
No, it's the armpit
no,
of the giant.
armpit of the giant, Ron.
Oh, give me a break. It's not the
Nope.
same as, it's not a variation of Beetlejuice.
Beetlejuice means armpit
Beetlejuice.
of the giant.
Armpit
Well,
of the
it's a corrupted version of an Arabic phrase of something like Beit al Jawza that means the armpit of the giant, or the
Yeah.
armpit of the central one.
And Antares, I know you guys all know what Antares means.
Yeah, rival to Mars. Yeah.
Yeah.
But now,
Arcturus, guardian of the bear.
other than Betelgeuse, how many of those do you think are supergiants that would be out beyond our orbit of the sun if they were here?
Antares, definitely, and Betelgeuse.
Mhm.
Yeah.
The others look more like main sequency.
Well,
Right.
there are some monster stars out there,
Especially
but
the
they're
blue
not on
one.
this. They're not that bright, I guess.
Mhm.
Because I
Well,
love
they're
seeing,
rare is the thing. The bigger a star is, the rarer it is by a power law. So if it's 10 times bigger, there are 10 times fewer of them.
Yeah.
seems
I was
to me
gonna
they,
say, last
you-
night when I was walking Wally around the house, I saw Procyon come up, again, before Sirius. And of course, it means before the dog. Yeah, Procyon.
before the dog.
Before the dog, yeah. And I was walking the dog.
So you were after the dog.
Yeah.
Dog following.
I love seeing those comparison videos on YouTube where it shows a Betelgeuse is a basketball, where our sun is a marble, and we're like a grain of sand. And then there's even one bigger than the basketball. Seems to me Canis, Canes, something.
YV Canis Majoris.
Yeah.
Okay. Is that the biggest?
No, well, no, there's one now. I forget the two. It's another variable star, so I forget the two letters in front of it, but it's in scutum, so it's something like WW Scuti.
But it's not on the. It's not one of the brightest here.
Well, this is apparent brightness, not
I
absolute
understand
brightness.
that, sure.
Right.
You don't have to be big to be bright. You just got to be close or
That's right, yes.
intense.
Yeah.
Mhm.
If you're up, you can see Canopus if you've got a good southern horizon.
Uh-huh.
2 in the morning, just roughly.
Yeah,
At
it's
that
very
point,
low.
it leads Sirius in the southern sky.
Well, that stuttering nova part of your talking points is fascinating to me, that there's a white dwarf in a binary system that's the size of the Earth, and it's sucking everything off of its giant companion that's less than.
There's the white dwarf down here in this illustration. This is not a photograph. The white dwarf is down here, and it's close enough to this big giant red giant that it sucks hydrogen off of the surface or whatever it can get. And that lands on the surface and builds up on the surface of the white dwarf until the material that landed there is thick enough, heavy enough, dense enough, and hot enough to start nuclear fusion. And then the white dwarf down here goes nova, and you get a nova explosion to it. And then it blows all the stuff off, and then it starts over again. And does it again. I think about for this one, I think
20 years.
20 years. Yeah, thank you. There's one apparently in Andromeda that explodes every autumn, plus or minus a month or two.
Really?
And because it explodes so frequently, it's probably close to the Chandrasekhar limit. That is as dense as a star can get. So the maximum mass of a stable white dwarf, which is about 1.4 solar mass limit. This star here that's illustrated is not quite that big. It takes a lot more material to add up, to pile onto the surface to get it to go critical. So it's a recurring nova.
Yeah, it doesn't destroy the star,
Right.
the white dwarf.
Yeah, it just causes these nice flare-ups.
Now, Jerry, you just said it's 1.4 solar units, but I have here, that's not the AU distance, so that's.
No,
So
that's
that's
the mass. That's how much material there is.
Well,
Right.
they're about 1.48 AU apart, so about
No.
100.
No,
That's, oh, really? Did I misread that?
Yeah, no, I think you're right, Ron.
1.48.
oh yeah, that's right. They are separated by 1.48 astronomical units. Yeah, but the mass, the star is less than 1.4 times our solar mass.
I'd be like,
Just a coincidence of numbers.
but it would be like one of them were in the asteroid belt, the other in the sun's location, right? That's about, would it be the asteroids or Mars or?
Mars is about 1.5.
Yeah,
Okay, got it. Wow. No wonder it's a tug of war. Gamma rays, too faint to see.
now the picture that you saw was pieced together from radio telescopes. And this is this is the largest steerable radio telescope on Earth, located at Jodrell Bank in the United Kingdom. It was also, I think this was built in the 50s.
Well, it's not part of a big VLA, very large array.
No, it's not an array. It's the Lovell Radio Telescope. It's a single telescope, but they did use an array. They used more than one radio telescope to develop that image.
And the really planet size array, this one probably contributed in that when they got the pictures of the black holes in our galaxy and in M87.
Mhm.
Yeah, that was a collective team.
That big bulbous part that looks like Epcot Center is part of it.
Yeah, that's part of the structure.
Okay, and it turns.
Yeah, steerable.
Yeah,
Okay,
this is an alt-az mount.
what's the difference between a single and an array? Array just gets the same thing. They're all pointed to exactly the same spot, and it just multiplies.
This one physically brings everything to a focus. The other one absorbs the signal and records the position and then times the signal to put it together into a single image.
Got it.
But the advantage of the array is you get an image with detail, with resolution, as though you had one dish the size of the separation between the dishes.
Right. Right.
Although
Here,
you don't get as
resolution
bright
is-
an image.
Say that again?
You don't get as bright an image as though you had one dish, but you get the
Right.
resolution.
Right. And this one is limited in resolution to the diameter of the dish. If you had another dish over here, the resolution would be defined by the distance between the two dishes.
Right. Yeah. Called the baseline.
Yes.
There's no way you could build a telescope, a regular one with a mirror that size?
This is a telescope with a mirror that size.
Well, that's a mirror? That's
It's
not,
a mirror, but it's a mirror for radio waves. It actually looks like a chicken wire fence if you're up close to it.
but it's metal, isn't it? It's not reflective. I mean, it reflects
It is-
radio waves.
It is reflective, but it reflects radio waves.
Aren't they building a monster telescope of about that size down in northern Chile?
Yeah, but probably not that big. 30 meter, that's like 90 feet.
Yeah.
They got some down there already. I wonder if it's among them. It's going to be in the same spot on the hill there in that Atacama Desert. Or
So
outside.
Yes.
Ron, it reflects radio waves to that antenna tip there that you see.
Yeah.
Yeah. Yeah.
Yeah, this is the focal point. That's
Right.
where the receiver is. It would be where the eyepiece is if this were an optical telescope.
Mhm.
And you remember on the
But if it were
RSCBO,
optical, huh?
go ahead, Ron.
Well, I was just wondering, the material is different for some reason. Why? I mean, metal reflects radio waves better than glass that's covered
But
with.
this doesn't reflect light. Our telescopes reflectors have a thin film of aluminum on it, and the aluminum is what reflects the light.
Mhm.
Really?
Yeah.
But the web is all gold. The
For
web,
infrared reflection.
Yeah. It has better reflection properties in the infrared.
part of the 10 billion they stole is that damn gold. There's a lot of gold on the web.
Well, it's a thin film on beryllium mirrors.
Yeah.
Oh, is it really? I just never seen that Epcot behind one of those before.
Someone pointed out, I forget the exact numbers, but the Palomar reflector, the 200-inch Palomar reflector, is actually a few ounces of aluminum.
Yeah.
Spread in a very thin layer and held in place by a figured piece of glass.
Mhm.
Well, they should put a roller coaster in it.
And you know, the Arecibo radio telescope was fixed. It was just a bowl in the earth, basically.
Mhm.
But there, they didn't have a spike coming up from the center with the focal point on it. Also,
Right.
it was spherical. It wasn't parabolic, so it didn't bring all the light to one focus. So they had those wires hanging over it where they could move the receiver
Right.
across and to where they wanted to point, basically. And then it had multiple receivers on it hanging down because all the light wasn't coming to the same point. All the radio waves weren't coming to the same point.
Yeah, James Bond killed somebody on that once.
Yeah.
Wonder what kind of pictures we got. They were all radio stuff, right?
Yeah, it fell down about a year ago.
Yeah.
Finally.
There's a bigger one in China that's operating now.
Mhm.
Gotcha. All right. Too bad you can't show us a picture from it, but what is this now? This is tied in with,
This,
The hologram.
This
Oh,
is
it's
a
time.
picture of a hologram.
can I start something real quick? I'll just read your fundamental questions, though we know lots of stuff. Here's what we don't know. Is the universe infinite? Goes forever? Does it have an edge? Where does it end? Is our universe all that exists? Or are there other universes with other physical laws? Gravity is reversed, maybe. A limited number of universes or infinite? You want to start with Stephen Hawking or Gerard Tahout and Leonard Susskind?
Let me first explain the picture.
Okay, what is the picture of here?
The picture shows a holographic image of a DNA molecule. Now, it looks like the DNA molecule is inside this, what is it, trapezoidal bowl. But if you reach your hand in there, there's nothing in there. It's just an image, and you only see the image from looking through the walls of the container. If you move the container, you rotate it slightly, the holographic image would change. You'd see it from a different angle. So, and the information, and you make this holographic image appear by shining a laser through the glass wall. So what is happening here is you're encoding three-dimensional information on a two-dimensional surface. That is, all the three-dimensional information of this image of DNA is in a density pattern or refractive index pattern that is printed into the side walls of the bowl.
Can I throw a little background on this so we know what we're talking about? 1995, which was what, 27 years ago? Holographic principle. Two, I guess, Europeans, Gerard Tahout and Leonard Susskind, came up with a theory saying our 3D world is just a constant hologram, leading to other stuff like string theory and cosmology. Yeah. I didn't know.
Leonard Susskind is a professor of physics at Stanford University.
Yeah.
And Gerard Tahout, his name is Dutch, I think, but I don't know where he practices.
Did they get physics award and Nobel Prize or anything?
No, they didn't for this, but they've received a lot of, they're very well regarded. I took a general relativity class from Leonard Susskind.
Apparently they started with Stephen Hawking's information paradox, which we haven't really talked about, but he said something similar, didn't he? Of radiation leak.
Well, the information paradox is that in physics, there's a principle. Information cannot be destroyed, it can only be changed in its form. If you take a book, the Encyclopedia Britannica, and you throw it in your fireplace, colloquially you think it's been destroyed, I can't read it anymore. But in principle, that book was written on the universe. And once it's written, it cannot be destroyed. You could, in principle, capture the smoke and from the pattern of the smoke, determine what was written in the book. I know that sounds pretty far-fetched and crazy, but anyway, the information paradox is that when you absorb everything that goes into a black hole, has information on it, and the information goes into the black hole, and then the black hole evaporates over a long period of time through a radiation effect called Hawking radiation. That is a particle.
And Ron, the information principle predates Hawking. Hawking is the one that came up with the radiation coming out of the black hole.
Right, exactly.
In other words, the black hole where light's not supposed to be able to exit,
yeah,
still evaporates on its own. That's kind of crazy in a way.
It does. It's a tricky way to do it, but it does evaporate on its own. When it evaporates, it simply goes away. Now, all the information that was in it was contained in it, and it goes away. So that violates a fundamental principle that physics regards as true. So either we have to change that principle, or they have to come up with a way of why information was not destroyed when the black hole evaporated. And the way that they get around this is they say, well, the information actually never went into the black hole. The information is coded on the surface of the black hole. And when the black hole goes away, this information is not lost. It gets back, it never went in, so it doesn't have to come out. So let's see where I was. So the Leonard Susskind and these guys came up with the fact that, well, that would be the case if all the information of whatever went into the black hole is really encoded on the surface like a hologram. Then what would appear to be in the black hole is actually encoded on the surface.
Can we say that information is also matter?
What this leads to is that the information is the ultimate fundamental particle. That is, everything will be broken down to information. And the key thing was of the Nobel Prize this year was that a particle by itself does not exist locally. It exists only by relationship to other particles. And so what that means basically is that the universe has an edge, and on that edge is a two-dimensional surface, and everything that we perceive as being in the universe is actually coded on the edge of the universe. And what we see, everything that we touch, feel, see, sense, everything is, as Albert Einstein referred to time as, a persistent illusion. Sound crazy, huh?
Well, we have our own produced holograms. So those are a hologram of a hologram. Holograms are
so a professor of physics at Lehman College in New York explained recently, and that's what I'm not getting this from the actual papers because I don't understand the subject matter that well to follow the math. So I have taken quotes from popularizations. So this Daniel Kabat at Lehman College in New York explained recently, he said, we're used to thinking that information about an object, say that the glass is half full, is somehow contained within the object. Instead, he says, entanglement means that objects only exist in relationship to other objects. And moreover, these relationships are encoded in a wave function that stands outside the tangible physical universe. In other words, things by themselves are not locally real.
Oh,
So this is all based on the puzzle. What Einstein didn't like about quantum mechanics is quantum entanglement, which has been demonstrated to be real. And he claimed that because of the consequences, that he said he just didn't like this, what did he call it? Fuzzy concept.
fuzzy concept.
Spooky action at a distance.
That's it, spooky action at a distance.
Well, amazingly enough, your vice president here sort of understands how holograms work. Tell me what you know about it. There are lasers positioned, like you just said, on the edge of the universe, but they're on the edge of the walls, aren't they? That
doesn't need a laser. A laser is how we make holograms in the lab. They were discovered when they had a soft, years and decades ago, they had a soft crystal. Barium titan? No, that's not it. But it was called a banana crystal, but I forget what the composition is. It was a soft crystal, and if you mushed it in your fingers, you'd get a banana smell. So they call it a banana crystal. And I forget it's 3 components or 4 components. But it could be altered. It could be altered by, yeah, go ahead.
Oh, I was going to say that's where the phrase monkeying around came from.
Monkeying around. So anyway, if you take a cube of this banana crystal and you shine a laser on it, and at the same time you shine a laser off a 3-dimensional object, and they interfere in the volume of the banana crystal, then you could go back later and you could shine the laser through the banana crystal and you could see the 3-dimensional object that you recorded in there. And as you rotated the banana crystal, the 3-dimensional object would present a different aspect to you. That is, you could actually rotate it looked like you were rotating the object itself. And these interference holograms are made use of in advertising. They're not particularly bright. They're not easy to see. But people in jewelry stores in Manhattan and stuff will put things projecting out of their windows like a hand with a diamond ring on it or something. And they're kind of dim, but as you're walking down the street, all of a sudden you catch this image in your eye and it looks like, oh my God, there's a hand right there. And then it's gone as soon as you look at it. But it startles them, and that's the effect they're after in advertising. So it works quite well. And they show the effect in various science fiction movies, like that game of monster chess or something they were playing on board the Millennium Falcon in Star Wars. Those were holographic images, but those were presented as much brighter than actual holographic images are. But the principle opened up a field of information theory, and there's a mathematical discipline for that too. And apparently that's what we basically are, is information. We're encoded patterns in the medium of organic molecules.
Well, I've been watching a lot of Matrix movies. Those Keanu Reeves,
Yeah, now that's not a hologram, is it? Or is it? That's more of a virtual world.
No, it all sounds the same to me. I'm sorry. It just, but I can buy it. Everything's an illusion. The fact that atoms are really not there, we get a ball, but it's all air or nothing, nothingness, and the electron, there's nothing to it, and there's.
Well, that's not exactly the right idea. See, when you take mathematical physical concepts that have very specific meaning, very exact meaning, and you describe it using colloquial sounding words, it can give you a confusing colloquial image. What it means is that the only thing you have for reality, even when you stub your toe on the coffee table in the middle of the night, and you're sitting there thinking, was that an illusion, or did I really stub my toe? No, you get all the benefits of it not being an illusion. But the fact is that all of the information that recorded, because you have 5 senses that receive information and send it to your brain, and your brain puts together what happened and what the world looks like. And there is a certain subjectivity to this, of course, but it's just information fed to your brain. and depending on your model of the world, you put it together, it's what's happening. But it's in a sense an illusion, but it's also for us in our world, it's very real. That is, your toe still hurts.
And what that implies is that everything that happens has been predetermined by whatever that information pattern is on the 2D surface of the edge of the universe.
Huh.
To me, anyway.
Well,
I'm not so sure I believe in determinism. But yeah, that's another.
But then you also have then this strange entanglement between us and the 2D surface.
Yeah. So it comes about when the final, like when Schrodinger's cat, the final state is defined by the observer observing the situation. And so the cat is then either known to be dead or alive. And well, that gets into a lot of fuzzy things that I don't really understand well. So I do not understand quantum mechanics to the level I need to really expound on this. But
can I just read one passage quickly?
Go ahead.
This is in reference to the picture that we're seeing right now, the double helix.
Yeah.
Juan Maldacena's duality principle, 1997.
Yeah.
He proposed this, as quoted in Jerry's notes. This special correspondence says the universe we see and experience as a 3D world is actually a hologram projected on us from encoded information onto the edge of the vessel. I assume that means the universe infinitely far away from us, so we can't see it.
Through the mechanism of quantum entanglement.
Yeah, that's what we've been talking about.
Yeah.
Okay, but this is all from the microscopic world, the quantum, which is different in many ways and butts heads with
many of what we observe as physical properties and stuff are emergent from the microscopic world. And the microscopic world in quantum mechanics describes how single particles work and small collections of particles. What we look at is the macro world and its massive, large statistical samples that behave predominantly a certain way. But individual particles, they don't affect us so much because they're small, but they behave more in general exactly as quantum mechanics would claim.
And Maldacena, I think, is the same guy that came up with warp drive, with a version of a warp drive.
What, instantly out to the speed of light?
Well, surfing on warped space-time.
Can we tie this in, gentlemen, at all with the Lawrence Livermore thing they just did? It could be pretty major.
Yeah, that's a different effect. That's the ignition facility at Lawrence Livermore Lab, where they had a laser. It used to be called Shiva for the many-armed Indian goddess, but it has a large number of lasers aimed at a single pellet of deuterium, and they all hit it wham. And I think this is where they got it, but they got it to burn, to actually fuse and produce more energy than they put in. So the fusion is actually occurring. And the fact that they got more energy out than they put in, and the lab is still standing, is a major achievement.
But they didn't actually get out more energy than they used generating the laser beams, but they got out more energy than they put into the point through the 192 lasers.
Yeah, good point.
Yeah.
So it's not going to be a viable alternative for the future?
When in the 70s, when I was in graduate school, controlled fusion was the power supply of the future, and the claim was it always would be.
Well, see, this is now they've transformed it to an engineering problem.
Yes.
They've done the proof of principle. It's a pretty complex way they do it. They put this tritium and deuterium pellet inside something called a hole realm, which is this strange shaped the gold capsule that it's inside of. And then they have 192 lasers that all focus into the ends of this hole realm. And it's shaped so that those lasers basically go through this sort of total internal reflection. So all our energy ends up inside that little tiny gold pellet, which I think is only like a couple of millimeters long. Okay, and then that heats up the deuterium and tritium to the point where the nuclei are moving so fast that they overcome electrostatic repulsion. Strong force takes over and you get fusion. So they did that with this one pellet, and it lasted, a couple of seconds, if at most. Okay. So now if you want to generate power continuously, you got to figure out a way to keep doing that. And you've got to really precisely position these pellets, and you've got to produce the pellets and drop them in there or stick them up in there in the right place. So it's a very complex procedure they went through, but it proved that you do get fusion and you can extract energy from it. It's mostly in the form, I think, of fast neutrons. So now you got to figure out a way to harness those and generate heat basically from that.
Okay, so get the heat, then you turn it into steam, and that runs turbos.
Yep.
That would be one way, yeah.
But I do have one big question about this that I never knew before. Maybe you could answer it. Fission, which is the splitting of uranium, let's say, or plutonium, that's the A bomb, gives us all kinds of waste and pollution.
Yep.
But fusion, which is even bigger, that's the H bomb, doesn't? Does that mean that
It produces helium.
Yeah.
I know that, but do you remember the movie with Gregory Peck called On the Beach?
Yeah.
Yeah.
Where they were waiting for the cloud after a distant nuclear explosion to come over.
Yeah, they only had nuclear winter in the northern hemisphere, and they were in a submarine in the southern hemisphere.
Okay, well, that would have been from fission bombs, but
Well,
That's right.
Run. The way we do fusion bombs is the trigger to cause the fusion, which in this case at Livermore is lasers. But in a bomb, the trigger to get the fusion is a fission bomb. So the reaction that's used in a thermonuclear bomb is called fission, fusion, fission for the really powerful ones. You have a small atomic bomb, a fission bomb, that compresses a sphere of, at least one way of doing it, a sphere of uranium or plutonium, mainly uranium, that inside there may be a plutonium. Anyway, you focus it to collapse this thing down onto some tritium or deuterium that fuses,
right,
and that produces fast neutrons that then cause this outer shell of non-fissionable uranium that you use to contain it. It converts that into fissionable material, which then fissions. So you get this triple effect that generates all the energy in a fusion bomb, and a really powerful one.
Ron,
yeah,
in the lab when this is all going on, they usually hang a sign there. It says "Gone Fission."
That could almost be, except that we were late starting, so we could probably got about 2 or 3 more minutes. It could be our epitaph for this version, number 95. But so the bottom line is you'd still get fallout, nuclear fallout from an H bomb.
From an H bomb, yes. Yes, you would.
Because it goes
not if it were controlled fusion in a confusion reactor, not a confusion reactor.
Yeah.
What did I do?
Well, it's kind of interesting that the 2 bombs are based on opposite ends of the periodic table, aren't they?
Yeah.
Uranium is huge, 235. I guess that includes the neutrons, and it splits open and sends out particles that kill us. And
that's the neutrons.
That's the neutron, all right. Yeah. And the H bomb or the fusion takes 2 hydrogen atoms and make them into a 2 proton, I guess 2 neutron helium atom.
Yeah. And 2 protons, 2 neutrons.
And technically doesn't send out any radiation. And that's why we wouldn't have, it's clean is what I'm saying, if we can make it work.
It's cleaner.
Cleaner?
Yeah.
So we do get an occasional radiation out of that.
Well, there's other, there's the gold hole realm in there, and you get these fast neutrons. So it's not totally clean. I mean, the neutrons cause the container vessel to get brittle in many cases over time. So there's a whole bunch of engineering that has to go into this, but it does not produce highly radioactive long-term debris the way a fission reactor does.
Right.
But do you suppose the future fusion plants might still melt down, or if there was an
No.
accident, they
No.
would never do it?
If stuff isn't perfect, it just doesn't work in this case.
Mhm.
Yep, the stuff falls apart and separates.
Well,
Besides, we can use the helium we're running out.
Yeah.
meanwhile, this looks like a great gift to send somebody if you can find one for sale. A picture on the screen. I'd like you to send me one, but
I don't think it's that hard to obtain a hologram and set it up in a lab.
well, how does the hologram of the universe affect the holograms we get in some theaters? And what is that a picture of?
The last topic is E.E. Bernard's catalog of dark nebula. But we'll do that next time.
Number 68, the Dark Nebula. Sounds like something right out of Star Wars. Gentlemen, happy holidays, happy fusion, happy shopping. Thank you. And we'll do number 96 or 7. I've got to get back on track next week. And we'll see you for all. When's the big trip to the Westmont Observatory? Is that coming up?
That was just Friday.
We just did.
Just had it. I missed it again. I'm all right.
And
Give them
for our
up your
listeners,
wives and happy holidays. Thank you, everybody.
Happy holidays.
See you later.
Happy Solstice.